Well, it's official, folks. With respect to this class, it's officially week 7 now. Next week will be midterms week, and it's a pivotal week in the sense that this is a week, or hang on, no. Yeah, that's about right. This is a week where I'm going to start getting all the materials settled up for the next upcoming exam. So essentially, whatever section we land on in this week here, just like we did for the preparation of exam 1, final section covered in this particular week will be the last section that can show up on exam 2. And exam 2, because we left off on section 2.4, it's going to start in section 2.5. But honestly, that's kind of a light section. There won't be too many questions out of there. It was pretty short as a lecture notes as well. But that's where we're at so far, folks. We're going to finish off section 3.4 today, and possibly likely 3.5 as well. This one was not as long as the section as I thought it could have been when I actually did the reading on this. So I don't have too many homework problems on the attached PDF for this one as the last one. But once we finish off that section 3.5, we'll be entirely done with chapter 3, our primer on logic. Well, any questions at all, folks, with where we're at so far? Or any questions whatsoever? Okay, well, let's get started then. We left off on example 5, and it was also a really long weekend. Predicates are really a new kind of way of thinking of logic. We only started last time. So let's do just a quick refresher. When we say a proposition, we mean a statement that's categorically, as it stands, with making no adjustments, it's either true or false. And that would be this one right here. Part A is a predicate because there are no moving parts here. Just 5 by 2 is 4. It's automatically false. And the falseness didn't depend on any other variable, for example. What makes something a predicate now is that the truthness or the falseness depends on some other element that comes from a different set U, which we like to call either the universe or domain of disclosure. And that's what's going on in part B. They look like similar equations, but this equation is definitely different. There's an unknown variable there. X can take on any real number whatsoever in the set R. And so this is not a statement that's categorically either true or either false. Its truthness or falseness purely depends on the value of X. And that's what makes part B here a predicate. Knowing the difference between the two of them is really critical because lots of different things happens with predicates that can never happen with a proposition. For example, we got into quantifiers, the universal and the existential quantifiers, right after dealing with predicates. Well, that's our 1 minute refresher of the difference between the two after a long weekend. Any questions at all, folks, telling the difference between? Okay, well, going on further, we kind of mirrored what we did in sections 3.2, 3.3 by doing these kinds of problems here where we're just evaluating the predicates, some problems where we did some translations or determining the truthness or falseness. And looks like we'd also did a problem where we took some definition from chapter 2, formalized it just using ordinary logical connectives and quantifiers. We'll be doing a little bit more of that in the very next section, 3.5. And finally, here's the translations part. We're on where we left off, example 5. So just another refresher on this one. P of X is the statement that X is an accountant. Q of X is the statement that X owns a Porsche. Here, we didn't directly say what the universe of discourse was. We left it implied. So that's why we just said for all X. We didn't say what set it came out of. We're just assuming we're talking about living people. The statement, all accountants own Porsches, and this is a really tricky statement, really, surprisingly turns into an implication type statement. Reading this all out left to right, it's saying, for all people X, if that person is an accountant, then that person owns a Porsche. So that's a direct translation of the statement that's above here. It also gives us a little bit of worry in the sense that we constantly mention that in this class, the implication logical connective, that one is really, really tricky. And this is just one of the other ways it becomes tricky. It's, to me at least, a surprise that a statement of saying all accountants is really giving us a quantified statement in this kind of way. Well, so far, We're now on part B where we're actually moving forward in the lecture notes. This one says, some accountant owes a Porsche. In contrast to where we said all accountants. All accountants means we had to use the universal quantifier for all, the upside down A. When it says some accountants, we use the existential quantifier, the flipped E. We'll say, there exists. There we said it, just with one symbol, the flipped E. There exists some X such that it says some accountant owns a Porsche. Well, this one's tricky, just as part A is tricky. Any volunteers for what should go here?
Wouldn't it just be the same as above?
Not quite the same as above. One person in class said, would it be, I think you said P of X and Q of X? Yeah, that's what would it be, what it would be in this situation. Let's write it down and see if we can track it through, because again, I feel like example 5 is a very, very tricky example. Oh, that was in fact eraser. So if we say exists X and put in the accountant statement, here's one condition on X. X is an accountant. And I like that you selected the AND operator. We want two simultaneous conditions to hold. And Q of X. Then we really have the essence of what this statement is saying. Some means there exists at least one. So down here we said there exists at least one person such that that person both owns a Porsche and is an accountant all at the same time. So there's Q owning a Porsche, P being an accountant, and the AND connective to me again is a big surprise on this. For this kind of statement, when there is two predicates, that for all becomes the implication, there exists, becomes an AND in this sort of situation. But does that make sense to folks so far on coming up with this logical connective? Awesome, thanks for the feedback on that. And yeah, this is a good set of problems to come back to. We'll harp on these quite a bit as we go throughout the textbook, because these sort of matters really aren't going away whatsoever. Next chapter is dealing with proofs, and dealing with proofs is all about knowing what the quantifiers are, if they are in the problem, how to find a counterexample, or just how to work with the statement itself. For example, knowing you have an implication here versus knowing that you have an and here makes all the difference if we're trying to prove a statement relative to these kinds of things. But I guess that's it for example 5. Let's move on to the next problem then. Big wall of text. Well, again, these are really just screenshots out of the textbook reading. Sometimes it's nice to have these all in one spot, but this is not necessarily a list of things that you have to have memorized, just a sequence of examples pretty much. We mentioned for a lot of these things, these are theorems, meaning these are statements that are going to be true for all the values X and S, and the values of the proposite predicates P of X or Q of X if it occurs in all of these. So these are statements that would always be true in the sense that we say here on the very first one, for all X and X, P of X and not P of X, or excuse me, or not P of X, that's got to be something that's always true, because either P of X checks as true. If it checks as false, this one would check as true. So we have a theorem in the sense that this is an always true statement. Doesn't matter what the set S is, this would always be considered as true. And lots of other ones. For example, we have the negations that we talked about earlier up in the notes, finally formalized here. These are De Morgan's laws, like we hinted at, the for all quantifier and the existential quantifier can be thought of as up here a long string of ands, down here is a long string of ors. And so De Morgan's laws from section 3.3, they just carry over directly. And lots of other curious stuff here. Our author got kind of involved with some of these statements, but here's a long list of statements that we considered theorems. Well, any questions, folks, with that big screenshot right here? Okay, so going on next, let's take a look at a couple more statements. We're going to determine the truth value of each one of them. Then negate the following statement, and express them using quantifiers. So this is kind of a fuller problem. Up in the notes earlier on Wednesday last week, we were doing this part right here, but only as a side comment, just getting ready to practice this kind of thing. So now example 6 is really mainly about using these De Morgan laws right here. So let's take a look at the statement, determine if it's true or false, and then negate it. It says, for all x in R, x squared greater than 0. How do folks feel about this one? True or false? Some for true. How about for folks in Zoom? How do you all feel about this one?
I say true.
Some for true as well? Awesome. You know, it feels true, but this one's actually kind of nasty in a certain sense. That for all x, the universal quantifier here, was actually very restrictive for the statement that's on the right, in the sense that this is true for every single real number, except 1, unfortunately. It's because it's a strictly greater than 0 statement right here. So my claim on this one is that it absolutely looks true when you read it, but then when you look at it and stare at it further, my claim is that it's false. Again, this is kind of a surprise. These quantifiers could be really very tricky. There's just one thing that's wrong with this that made it false. So if it's false, we have to be able to say exactly why. Here's the proof. It's going to be a proof by counterexample. Let's say it this way. We mentioned this proof technique just a little bit, but the only reason we're saying we want a proof by counterexample is because we're trying to prove this whole statement is false. And only one value of x that makes that predicate a false statement would be just showing the falseness by a counterexample. So we pick the one and only x that could be a counterexample, let x equal 0. Again, that makes this kind of a cheesy problem. It was really close to being true. If we put in greater than or equals to 0 like that, it would have been true. But without it, there is an exception. If x is 0, then x squared greater than 0 becomes 0 squared bigger than 0, which is false. Then we can just end this whole argument. That little double slash there is just a way to say we're ending the statement starting with, we're giving a logical proof of why this has to be false. And this is it. For a for all quantifier here, one example that negated the predicate statement here, showing that that statement is false, did the whole job. That means if we go to negate the statement, this is the part B to the problem essentially, the statement that we get through the negation will be absolutely true. So that's what we're going to do next. First, any questions at all, folks, with determining the falseness? Okay, let me just write down our next part. Negate the statement means take this whole statement for all x in R, x squared greater than 0. Here's the negation. We can say it's logically equivalent. First, De Morgan's laws over quantifiers flips the for all into there exists. So there exists at least one x, such that we also have to negate the statement. Well, if we negate that whole thing, you could visualize it this way. Negation of the statement, x squared greater than 0. It's kind of a funny way to visualize it because we're used to seeing either a proposition or a predicate right here, written out as a p of x or q of x. But you know that is a predicate in its own right. We can negate it and say, this is now logically equivalent to there exists some x such that negation of this will take us to x squared, flip the inequality to less than, include the possibility of being equal to 0. And that's a believable statement. The x that makes this true is 0. 0 squared is less than or equal to 0. It's that extra inequality right there that makes a statement suddenly true. We expected the truth of this after we negated it, It's a good idea to do another mental check here just to make sure it is actually true. So we didn't make any weird, silly mistakes in the middle. Well, we did it, folks. The purpose of this big chart up here is really the De Morgan's laws for the quantifiers. We just use the first row right up here, and that's the result. We'll try it again on another statement, and then that finally fills out the rest of the 3.4 notes. We'll go into 3.5 after. So here's the next statement. This one is an existential quantifier. It says there exists x, an integer, such that x plus 5 less than or equal to 3. Well, how do folks feel about this one? True or false this time? If you felt true, but you weren't too sure because the last problem was kind of a tricky surprise, I would understand that. But this one turns out is definitely true. Probably the more confusing thing about the notation is z there. Recall that's all integers, whether positive or negative. We're excluding fractional values, irrational numbers. My claim on this one is that this statement is true. And like before, to really show it's true actually doesn't take too much work. Because that's an existential quantifier, we can say proof. Just one value of x that makes this true is enough to say there at least exists one x that makes it true. So in other words, we're just finding at least one. We can say take, how about -5? Why not? Set x equals -5. Then x plus 5 less than or equals to 3 becomes 0 less than or equal to 3, which is true. So that ends the whole statement. With an existential quantifier, if you want to show the statement is true, just come up with one example. -5 did the job, and 0 is less than or equal to 3 says, yes, it is true there exists at least one x fulfilling this inequality right here. So that one goes pretty fast. Next thing we'll do is the negation. But any questions to this stage so far? Let me see if I can fit this all into one page. There we go. So next is the negation. Because we said this is true, when we form the negation, we better come up with a statement that is false. So let's write this out. Negate, there exists x amongst the integers, x and z, such that x plus 5 less than or equals to 3. So upon negating that, we get a logically equivalent statement. No harm if you used equality here, but it's always a good call to use the actual triple bars to say this is an abnormal kind of inequality. But first thing that happens is the quantifier, whatever it is, always flips through negation. So if it's an existential, it becomes the universal for all x. In the integers, z, we'll flip this one. And two things always happen when we flip an inequality, making it a little bit more tricky. The direction changes, and if it was a strict inequality like this one, strictly bigger than 0, it becomes a sharp inequality, less than or equals to 0. And if it was that kind of sharp inequality, less than or equals to 3, it has to flip and become strict again. So this will be x plus 5, strictly bigger, positive 3. So that would be our statement right here. Here we went through that step and negated the inequality as well, just to save a little bit of space, I suppose. Let's say see if this is even true. For every integer in z, if we take x at 5, it's got to be bigger than 3. That definitely looks false. For example, if we took, say, how about -5? That's an integer in z. And if we put -5 there, it would say 0 bigger than 3, which is false. It's the for all x universal quantifier right there that's making it false. It was the existential quantifier right there that made the original statement true. It's kind of nice. The proofs are kind of fast, but let's put in one additional comment about that before we go to the next problem. Any last questions or comments at the moment, folks? Okay, so example 6 consisted mainly of things that were just easy to show as false, easy to show as true. But one additional comment that deserves to go along with this is the following one. Let's say to prove for all x, I'll just put a generic predicate, p of x is true. In the prior problem, we showed that that kind of quantified statement is false. So we just needed one counterexample to demonstrate the falseness. But if it were true, another important question is, how would you show it? To prove it's true, we must show that p of x as a function that outputs either truth or false will only output true for all x. And let me widen out the statement just a touch. Let's write for all x in U, just to make specific what we're referring to. When we say for all x, we mean in the domain of discourse. For all x in U, which means we can't pick just one and show p of x is true. We have to work with x generically. Well, we'll come back to these kinds of topics when we are dealing with this in the next upcoming chapters. But for the next, we'll do an application and move on to the next section, 3.5, with nested quantifiers. So here's our big application. This is an application from calculus. So if you haven't taken calculus yet, I'd say don't worry about it too much. I can't ask this question again without it saying, say, example 7 or something. So this one is purely just an application. The goal of this problem is just to connect what we did in section 3.4 with what we're about to do in section 3.5. And even if you haven't taken calculus before, this is the very first definition in most calculus classes. So we'll cover just exactly what this is saying. Okay, so let's give this a try. What we're reading out here for our first definition is a limit statement. It says, suppose f of x is defined when x is near a. Then this whole statement, read as the limit of f of x as x tends towards a equals L, means we can make the values of f of x arbitrarily close to L, so the function values are getting as close to L as you like, by making x sufficiently close to a. So as x get closer and closer to a, we're saying the values of f of x are getting closer and closer to L. So we want to re-express all of that using quantifiers. And it's kind of tricky, this part right here. The less tricky part is visualizing what this is going to say, but we really need both to help us reformulate this in quantifiers. So to start out, let's begin with just a quick plot so we can organize our thoughts. Really, this is kind of an application in just reading any bit of mathematical material. There's levels to reading this stuff. There's reading it ordinarily like we just did, but if you're like me, you might not have gotten too much out of that. It's just a lot of words. There's a lot to keep in your head all at once. The second level to reading this is taking everything that's said here, try to sketch out a graph that captures the spirit of the definition. If we can do that, there's more understanding in our head. And then if we read this out again, it'll start to make more and more sense. So let's get really close to these elements. Suppose f of x is defined when x is near a, except possibly at a itself. So f of a could be undefined, and this would be okay. I don't want to draw a weird graph, so I'm going to let it be defined at a. It's going to take on some value through here. And here's the graph of y equals f of x. I'm going to say it starts right here, so it has a finite domain going to the left, moves to the right forever, so infinite domain going to the right. We have a value right here, but what we're mostly interested in is L, the output to the limit statement. So we can drop that in there. We also have A coming from the limit statement. And so this is the graph of f being defined near a. And the next part says, as x approaches a, the values of f of x get arbitrarily closer and closer to L. So we need to add that next element to the graph. We take an x that's close to a, we're imagining it's getting closer and closer to a, either from the right or the left. It wasn't specified, so both had to happen at once. Let's pick one at the right. Let me try again. Let me switch to a pen. Here's my value x. Right here. The moment we put down a value x, we can put down a point here. This point is going to be at height f of x, and we're just about there. So it says, as x gets closer to a, the function value of this point will get closer and closer to that point there, which means the height of the graph, f of x, would be getting closer and closer to L altogether. So this is the second level of reading this whole definition. We see what's going on in the graph. We see what's being expressed. Now we want to take everything here, the definition, what we see in the picture, re-express the definition of limit only using quantifiers. Any questions at the moment first, folks, about the graph or otherwise? Okay, now, before just jumping into the quantified statement, notice it says right here, if. That's really tricky in a certain sense, because if there's an if right here, this is the hypothesis in an implication statement, if P then Q. So let's take this whole thing right here, deserves some good highlighting. Let's call all of this the P of X statement. Definitely emphasizing the if that goes right there. So that's the hypothesis of the if P then Q. And it says here, by taking x sufficiently closer to a, but not equal to a. Oh, hang on. I think I'm getting a little bit mixed up on that if. Yeah, definitely getting mixed up on that if. It goes a little bit backwards than I thought, so let me try again. Trouble with that if was, I was thinking if P then Q on there, but actually goes backwards. That if is written out literally verbatim from a real calculus textbook, but that if is a misnomer. This is going to be the conclusion Q, rather, and taking x to be sufficiently close to a, that's going to be the predicate P over here. So I think this is a better way to organize it. Let's drop this all back into the fully quantified statement and get started. So if I think of this as the P of x, we want to take x to be sufficiently close to a on either side of a, but not equal to a. We can say here, first, for all, well, let's maybe think of this right here. We're also trying to make the values of f of x arbitrarily close to L. Arbitrarily close means within any small positive distance. So if we want f of x arbitrarily close to L, we can begin by saying, for all epsilon bigger than 0. Then write down a next statement. But this is really kind of confusing. There's an implication in the middle, and there's another quantifier out of nowhere, taking x sufficiently close to a. So we want to say f of x is going to be getting closer and closer to L if x is closer and closer to a, so we need a whole new quantifier. It's going to be an existential one. We'll say, once you pick the distance that f of x is going to be away from L or within, so within a distance epsilon, there needs to be another distance that x has to be away from a so that f of x really gets within epsilon of L. So there's going to exist a delta bigger than 0 such that, let's write out this, if x is close enough to a, well, we'll use that delta statement. If, rather than writing if, let's just put in this statement here. I'll connect it with that as the if. So this is the if some condition, then some other condition Q. And we want less than 0, greater than x minus a, less than delta. So this is going to be the P of x statement. We want to take x very close to a within a small measure delta. This is either side of a, so that's why we need absolute values. It can be in this picture, or x can flip around. Still, we're within that distance. And when it said not equal to a, we also put a greater than 0 to exclude the whole possibility x equals a itself. All that to say, if x is close to a, then f of x has to be close to L within the distance epsilon. So we'll go next statement, f of x minus L less than epsilon. So that's finally the Q of x statement. Got those backwards when I was trying to think of these right away, just dropping here into the problem, but that's again what the graph is for. It goes backwards than the authors even indicated. The if is really if x is sufficiently close to a, if x is sufficiently close to a, then f of x is sufficiently close to L. But each time we say sufficiently close, we need to say exactly what we mean. The for all epsilon here is allowing us to get within any distance of L that we would like. So any positive number, think 0.001 scientific notation might have to be used. But for every epsilon, there is a delta. This delta is a function of epsilon, in the sense that once you pick epsilon, a value of delta has to be determined. Change epsilon again, a new value of delta has to be determined once again. And all this is saying f of x has to get closer and closer, lower and lower to L. X itself has to get closer and closer to A. So the delta values are changing as well. So this is the landscape that we're in section 3.5, really the whole goal of the application. To show what can happen with quantifiers, they can just keep on stacking and stacking up. And statements that are very, very common in mathematics, like this one, is already a doubly quantified statement. And we'll take a look into a lot more in section 3.5 when we're practicing it further. But this is the major thing that I want to demonstrate, that these kinds of definitions are really kind of tricky to track in your mind, to visualize in this way, and extra tricky to just put down on paper as a fully formalized logical statement. But if you can do that, that's a really tremendous way to internalize this kind of stuff. So again, this is more of an application, not on calculus or limits whatsoever, but more just an application on reading mathematics in the first place. We'll do another similar style kind of application like this in section 3.5. But for the moment, looks like we're done with this section. Any last questions or comments whatsoever, folks, before we turn to 3.5? Okay, I think I got that saved in. So here's our last section in chapter 3. Kind of sad in a way, it's kind of a fun chapter. Oops, let me fix my windows real quick here. Okay, well, section 3.5 really does not have any new definitions. It's kind of an odd section again. It just is really extra information that ties in with section 3.4. So just for the sake of making them visible and readily to work with, we are redefining universal quantifier, existential quantifier, just a direct carryover from the section 3.4 notes. And now we want to start writing down more statements like the application problem we were just looking at, using quantifiers. This time, however, we may have to use many quantifiers. We have to kind of go here carefully and see exactly what we're getting into. First goal in section 3.5 is to do some translations. Ordinary statements like these, just like the last application, we want to write down using quantifiers and any other logical connectives we might need. It says the sum of any two positive real numbers is positive. I believe that statement, and now let's begin by putting in, well, it says any two positive real numbers. There's a lot of ways to go at this. But one thing we can do is inherit some of the notation that our author laid out for us in chapter 2. We can start by writing down, for any, we have a universal quantifier for all x. It's a positive real number, so we can indicate the domain of discourse by saying, for all x in R, that asserts it's a real number, but if I need to say it's positive at the same time, our author introduced this notation, greater than 0. You have to be careful though, because saying positive real number, R greater than 0, is not the same as a set as R greater than or equal to 0, and sometimes that can make all the difference. This is the non-negative real numbers, and this is strictly the positive real numbers. Feels the same, but there's one number difference between the two of them. So we have one positive number for all x in R greater than 0. We can put in another quantifier. There exists at x. Well, shouldn't say there exists, right? Because it said any two positive real numbers. It didn't say for any positive real number, there exists another real number. So let's backtrack off that statement. This one's quantified universally by two universal quantifiers, for all x, and again, for all x. In R, strictly greater than 0. If there were even more quantifiers, we just keep on adding more of these structures and write out the statement. What we'll do next is just say the sum of any two real numbers is positive. We already have the positive real numbers, so just go x plus y greater than or equal to 0. And we did it, folks. This is the entire statement written out using logical connectives, quantifiers mainly, 2 of them this time. Any questions whatsoever, folks, getting this written down? Good question. I think I did a micro sleep on that one. So that X right there, thanks for spotting that, should have been a while together. Let me see if I can delete that in an easy way. There we go. Just highlighting my mistake there. Thanks for spotting that one. For all x in R, for all y in R, x plus y greater than 0. Now it makes sense. Without y defined what its domain is, whether it's quantified or not, whole statement would have been just nonsensical at that point. Thanks for that fix. Other questions so far? Okay, definitely a true statement. This is just a property of real numbers. If you add two things that are positive, no possibility for it to flip to negative. So this is true. And again, just for the sake of practice, the problem didn't ask us to do this. Well, let's negate this. We've not negated a doubly quantified statement before, so let's do just that. So negation of, for all x in R greater than 0, for all y in R greater than 0, we have x plus y greater than or equal to 0. And, you know, thinking about how I wrote down this again, it's true that x plus y greater than or equal to 0. That's not really the spirit of what they were asking us to directly say, right? One more fix. When they said is positive, just like the comments we were making over here, they were meaning strictly greater than 0. So let's follow that to the letter and go strictly greater than 0 in that way. Highlighting here to highlight that second mistake, and it carried down over here. There we go. I don't think I would have been that picky if I was grading this as a homework problem or exam problem, but it's interesting to know, and it's a decent challenge to try to get the statement down as close to verbatim as you can. Okay, back on track. Our goal here is just to practice. So the bar here is just to say this is an additional comment, not something you have to do on your homework. But for negating a doubly quantified statement, same thing as what we did last time. We just flipped both of them now. So we can say there exists x and R greater than 0. What flips is the quantifier. Nothing about the set can change. So even if it's greater than 0 there, we can't change that inequality whatsoever. it must be the same exact domain of discourse for X. But we'll flip that quantifier to an existential one. There exists Y and R greater than 0, such that X plus Y less than or equal to 0. So that's the fully quantified negation. Again, that almost looks true, except our domains of discourse excluded 0 for both X and Y. So now there's no possibility for this to actually equal 0, making it true. It's patently false now. Well, any questions at all, folks, with quantifier negation? Oh, hang on. I'm reading my work here a little bit more carefully. Negate the statement written in A using quantifiers. I should have just put here, exists X in R greater than 0, exists Y in R greater than 0, X plus Y less than or equal to 0. That was really bad strategy for doing a problem like this. Well, definitely read the whole problem so you don't do what I just did there. I'll clean up the notes later after class, but any questions so far? Okay, so that's how example 1 went. Kind of a nice statement, a little bit tricky. Watch out for the things I highlighted though there. Those are my personal mistakes in trying to write it out with quantifiers. And now let's just try it again. Might deserve a new page. Let's give some extra space on this one. This one's now going backwards. We have a quantified statement, 2 quantifiers altogether, so nested quantifiers, an inequality like before, n less than n. All we want to do is now restate the following using ordinary words. And it could be just as much as going left to right and just literally reading out what you see in ordinary words. For example, where the red dot is here, you could say for all. For this portion, you can say elements M and R, or just simply M in R. I was thinking of writing it out this way. But if we want to write out only using words, let me back off even that and say for all real numbers M. Then the next part will say there exists a real number N for this part, I would just read out for which, or you could say such that. I'll go with the such that on this one. Such that the integers that we defined would satisfy n less than n. So n is less than n. If you wrote m less n, I think that would be totally fine. But following the instructions to the letter, we wrote down this entire statement using ordinary words. Does that look right to folks with that statement there? Okay. I would say that this is true. If it weren't true, we would be saying that for all real numbers m that you can come up with, there is some other number n for which m is always less than n. If we are accepting this as true, it's a way of us saying there is a largest real number, which is absolutely false as well. So now we know this whole statement on its face value is a false statement. Let's say here, false. No. Well, hang on. I think I've read that backwards. I feel like this is true now that I'm looking at this a little bit more carefully. We should be able to argue that though. It says for all real numbers m, there exists a real number n such that m is less than n. Yeah, no matter what real number you pick, I can pick one bigger. I would say that that's a true statement altogether. What kind of makes this a little tricky is if we reverse the order of the quantification on this one, for example, you said there exists an n in this place, and for all m in this place, now you've got a pretty weird statement. That's what we're going to do down below. So let's see what happens here. Any questions at all, folks, with thinking about this one, flipping it from false back into true? Okay, let's do the negation of it then. So negate the statement. We're negating this one because we want to write out using quantifiers. We may as well start with a quantified statement. So for all n in R, there exists n in R such that m less than n. So we're expecting something false. Let's see if it really happens. Oops, didn't mean to throw my pen. There it goes. For the first one, for all becomes there exists m in R. So some real number m such that, now this one flips, for all n in R. This flips as well, and we change from a sharp inequality, or excuse me, from a strict inequality to a sharp one. M is now greater than or equal to n. And this is our new statement. We said it's false, or excuse me, true up here with a change. Then this one should be false. Let's read it out in our mind. It says, there exists an m such that for all n, m is always bigger than that real number n. This is asserting that m is the largest real number in existence, because for all n in R, n is always going to be smaller than n. So yeah, this is the statement that is absolutely false. And this is the one that was true. It's kind of funny when you read these out or write them out for the very first time, easy to kind of lose your way and get a little bit turned around and backwards in your own head like I just did. So these are ones you should really read out twice. Spend some time with it. Make sure everything really makes sense. Consider the negation. Make sure it really seems false and all that kind of stuff, because it's easy to kind of trick yourself. But we did it, folks. This is two kinds of translations. Examples 1 and example 2 kind of opposite of each other, and then a negation down below. Any questions so far with getting through any one of these? Okay, a lot of these are kind of warm-up problems in a certain sense. And what we're moving towards is this kind of stuff. There's a couple of problems like this in the homework set as well. I believe one of the examples in the book and the reading does problems very similar to these as well. We want to take these old definitions that we looked at, we studied back in chapter 2, which feels like a lifetime ago already, and totally redefine them now using quantifiers. So we'll do that for the definition of a function itself, a very important object. We'll do it again for the sake of practice for onto functions. The homework is going to be for one-to-one functions. Then we'll try another translation it looks at like, and this will be the big application that we're going to go for. Because we're getting closer and closer into proof techniques, we're going to look into other information dealing with coding and stuff like that. This will be our first example dealing with pseudocode. These are pretty open-ended questions as well, so we'll take our time with this one when we get down to it as well. But for the moment, this is the major things we want to talk about with quantifiers. Now we're just applying them to typical kind of problems. Well, any questions at all, folks, before we get started? Okay, well, here's our definition of a function again. And like we mentioned before, there's lots going on when you read out a definition like this. It says let A and B be non-empty sets. Great that they said non-empty here, because we don't want a function with an empty domain. It would have no meaning any longer. A function f from A to B, written this way, assigns to each input value x in A, a unique output b in B. The unique value b assigned to A is denoted by f of A. And we sometimes say either that equation or just verbally, f maps A to B. It looks like the real meat of this that makes the definition of the function is this part right here. The rest of it is just notations or telling us how we say certain things, write them down. And this is just clarifying the role of A and B, giving further definitions. We want to restate the definition of a function, and that's really where this sentence starts, primarily the highlighted portion right here. So let's give it a try. It says assigns to each input a value, each input value, X and A. So we're going to start with X in A. And now when it says assign to each, does that feel like universal or let me try again on that one. It's supposed to flip, there it goes. Existential. It's going to be relative to this word, to each. Anyone see which one it should be? Let me put the red dot in a neutral spot. I agree, absolutely. To each, for every, these are all ways of saying the universal quantifier for every value X. So we'll pick out that one and write for all X and A, the domain, it says there is a unique output value B in B. This one's a little bit tricky when we say a unique output value. So there's going to be a couple ways to write this down. But, you know, the major thing we have to decide is we're talking about another value B and B, but are we talking about one B value or all B values when we say a unique? In other words, for this one, is it for all or is it exists? Any volunteers to determine the quantifier on this one?
Would it be existential because it has to be a different one every time?
Yeah, absolutely.
Okay.
When it says a unique, that's a great way to think about it. It has to be a different one any time. And we're not talking about all of them any longer. We're talking about exactly one. You know, it's not even perfectly an existential quantifier. We have to roll in the fact it's unique somewhere in our definition as well when we go to write this down. But good call. This one is absolutely an existential. So now we're saying for every value in the domain X and A, there's a value in the codomain B and B. So here's our codomain. Such that, well, we have to make sure we capture the fact that this B value is unique somewhere. But the thing that happens for all X and A, there exists a B in B, is this, F maps A to B. We can use that formalized notation here and just write function notation, F of A equals B, but that's not the whole story, right? We need to throw in uniqueness to this, so let's do it in this way. F of A equals to B, and here's a strong condition, and it has to be because we're saying two things at once. There exists something, and that something, the value B and B, is unique at the same time. If you wrote here, B is unique, you know, I'd say that would qualify for a solution. It's honestly sort of a cop-out because our goal is to use only logical quantifiers and not write down too many sentences. I would say that this would be an acceptable solution. Let's give two solutions though and say that this is solution one. But I think we did it, folks. In solution one, we're saying here, for every value in the domain A, you can find a value in the codomain B, such that F maps to B. But to really make it a function, that spot here, B is unique, is very critical. So let's go to solution two. The whole goal in solution two is to formalize B is unique. I think solution two is more in spirit of what example 3 is trying to do in this section. But again, just to emphasize, if you left it out on this way in solution one, this is for full credit as well. So we need to assert that B is unique. How can we do that? Well, let's try out here. B is unique can be stated as if f of A equals B, and let's say f of A equals a different B value coming out of the codomain B. Let's say beta, might as well go to Greek if you want something like B, but slightly different. So if f of A equals to B, f mapped A to B, and if f maps A to beta as well, but B was supposed to be a unique value, then B has to be equal to beta itself. So this is one way to say it. If these two conditions hold, then B is beta. The output value was unique. If something maps to it, then map to it again by the same input value, your outputs had to have been the same. This is just by the nature of being a function. And if you think of a graph, this is essentially just the vertical line test for determining if you are looking at the graph of a function. Okay, well, this is an ordinary statement in its own right, so we can say that formalized, we can write this as let's use this as the hypothesis and implication, f of A equals B, and f of A equals beta. This is the whole P in a P implies Q statement. This is the Q part. It implies B equals beta. So here's P, here's Q, in a gigantic if P then Q. Does that make sense to folks so far on the uniqueness portion? Kind of a heck of a word, right? That one word, unique, took something that was kind of short in solution one, that's making it really, really large. This is uniqueness quantified now. So overall, we can say for solution two, we have the function if for all x in A, for all x's in the domain, there exists B in B, there exists an output in the codomain such that lots of stuff has to happen. So I think color coding is a good idea at this point. Let's take this whole thing, call that blue. Let's make this green here. Start with the mapping part. F maps A to B. Hang on. I have a problem with my A here. Written out slightly better, it shouldn't say A here. And let's see what that should have been as opposed to an A. Good call on that one. That's the same mistake I made from earlier. Sorry about that one, folks. Let me use this color pen to just track through that. We're talking about X. Should have been X right here. Oh, then color coding is going to make that slightly problematic. And then down here, should have been an X as well, and an X as well on that spot. That's one way to fix it. I could have just put an A right there, and that would have fixed it as well. So with that fix, let me think of this as the whole portion that was in green. Here's the whole portion that was, my fix doesn't really show up like that. Here's the whole portion that was in blue. And now we could say, finally, for all x in A, there exists a B in B such that f maps x to B. So f of x equals B. And that output value B was unique is this whole statement. F of x equals B. And f of x equals beta. Let's see here. I want that part. Let me first fix penmanship. I want that part in brackets and then says implies B equals beta. But just for the sake of extra clarity here, let me put in an additional bracket going this way, ending here. So it's this condition, the mapping, and this condition has to hold simultaneously. The uniqueness, this is the worst part about it. And this works for all x and a. Once you determine an x, b is a function of x in the sense that you have to find the specific value b that's going to make this mapping work. But this is another view of what we mean by a function, kind of a pain when you write it all together. And when you think of it in ordinary words, that part right there, which is the most important part about being a function, it gets kind of lost in the translation. Writing it down in quantifiers really highlights that that's a big part of it. Even if you win the solution one, it's got to be there some way, somehow. But any last questions, folks, on the challenges of quantifying these kinds of statements? Okay, well, for extra practice, let's try onto functions next. The homework problem is going to be about one-to-one functions. If you have any questions when you're writing those down, don't hesitate to reach out either in office hours before or after class, or say, I guess those are the options, email as well. I'll be happy to help out with it. This one we're dealing with just onto, and it says here a function mapping a to b is called onto if, notice where the for every is now. The for every is relative to the codomain b this time. So for every b and b, there exists at least one element a in a for which f maps a to b. So this is kind of nice when it says at least one. We don't have to be so specific. If it said exactly one, then we're dealing with the uniqueness issue here that took a lot of extra work. So let's write out this here. So onto if starting here for every b and b. So onto-ness is really focusing on codomain. Essentially what we're trying to say is the codomain is the range. So you pick a b value, but this has to work for every single one. We can't pick a specific one. So we use the for all quantifier. For all x and b, let me write out this way. Let's match that notation. I think that will eliminate some of these weird mistakes I've been making. For all b, in the codomain, uppercase b, it goes on to say, there exists. And it did say at least one, but all it needed to say is there exists x and a, and this meaning is exactly the same. So this, literally fluff. We didn't need it to write down what we needed to write. So we'll write down here, exists a and a, so now value coming out of the domain, such that f of a equals b, or f maps a to b. Then, I guess that one was kind of nice. This is totally over. That's all we had to say. This is onto-ness. Oh, any questions so far? Okay, kind of a weird process because, again, when you think about one-to-one or onto, there's the definition, there's the graph of what it all looks like, and then there's the quantified statement. But if you can see this three different ways, again, that's a really great way to enforce and really understand what is onto functions really all about. So this is just another way of expressing it. And it says on part B, by negating the statement in part A, express what it means for a function to not be one-to-one, or excuse me, not to be onto using quantifiers. Well, what we mean is we're going to put a negation in front of this and also crank out the result, giving another logically equivalent statement altogether. Really kind of what we did at the start of the notes. Those were a warm-up, and now we're doing it for this entire statement. Negate for all b and b, there exists a and a such that f maps a to b. So on the left means we are onto. On the right means we're going to not be onto. On the left without the negation symbol, I should have said. So now when the negation takes over, just visualize this distributing through, flipping things around, negating statements. Flips all the quantifiers, so this is now exists B in the set B, such that, flip this one, for all A in A, this one right here will be f of A is not equal to f of B. Well, this is the negation of the statement above. It says there exists an element in the codomain such that for every element in A, the domain itself, you will never get, oh, f of A equals to B. Sorry for that mistake right there. That should have been f of A not equals to B. I think I was thinking of 1-to-1 when I wrote that down. And yeah, that's what not being onto means. It means there is a codomain value for which no value A in the domain can ever map to it. So we threw a not equals on there. And this is now not onto. Well, any questions at all, folks, running through this one? Okay, well, we're nearly done with this section. I only have a couple more examples I want to take a look at, but maybe some other takeaway points on this. We focused a lot on what goes on with the negation, but also keep in mind, nested quantifiers are sometimes commutative, but they're often not commutative whatsoever, in the sense that on this one, if you change the order for all x in R with the for all y in R, you have the same exact statement. It's because the thing on the right is symmetric, but more importantly, it's also because for the universal quantifiers, you can swap the order of these if they're stacked in this way. Same if it's a bunch of existential quantifiers, but when you mix them, say for example, on the one we're just looking at, mixing the order of these, just taking this whole part and dropping in front, absolutely will change the meaning. So if we have mixed quantifiers, the order of the quantifiers always matters. Let's say it here. For mixed quantifiers, for mixed we mean existential with universal, the order of quantification matters. Change the order of quantification and you have just a totally different statement for these types of quantified statements. And now for the next things we'll do is take a look at these kinds of problems. We're going back to defining a predicate, defining ordinary words. Person X is a parent of person Y is going to be the meaning of P of XY. We'll write down logical statements. So we're doing translations going from English to quantifiers using the predicate P of XY. But really the kind of purpose to this example 5 right here is it's a warm up to the application over here. Same kind of a situation. We have a predicate that takes 2 inputs. So it's a binary input here. We want to rewrite this using quantifiers. But this is the major application down below. Using pseudocode, we'll also re-express what our quantified statement is trying to say. In other words, if you have to implement the quantified statement into some kind of system, what would your actual syntax look like? First, we'll give this one a try, and looks like we'll come back on Wednesday's class to finish up the application, move into chapter 4. Well, let's give this a try. P of XY is the predicate. Person X is a parent of person Y. We'll write a logical statement using quantifiers, standard logical connectives, to know each of the following. First one, it says, every person has a parent. Now, we mentioned a lot in the last section. When we go to write out quantified statements, we like these things. Those are the domain of discourse. If we left them off, the domain of discourse has to be implied. So it's really up to you how you'd like to do this problem. You can leave off the domain of discourse, but I'm going to go the route of writing it in. Let you be, let's see, we're dealing with people, but this is about being a parent of person Y. So we don't want you to be all living people. We just want it to be all people that are either living or deceased. All living or deceased people. So we have a domain of discourse. And if it says every person has a parent, one way to write this out is to begin by saying, for all, well, I could use X's and Y's, but that can be kind of confusing up here with the change in the notation. It's a bit of a conflict. Kind of a problem I've been struggling with all day today. So let me change this up to an A. That way I can just think of this as a new meaning. I want to say, for all A in U. So that's going to be every person. I want to have another domain of discourse for, let's say, all the parents. Let's say T equals all people that are parents. Just like with you, we're not too concerned if they're alive or dead, as weird as that sounds. We're just interested in the relationship. Person X is a parent of person Y, so we can take into account centuries of historical data. So we'll say T is all people that are parents. Actually, let's change that to P. I think that makes a little bit more sense. Alive or dead. So if you're a parent, you're a part of this set. Okay, so now back on track. Every person has a parent. We can start by saying, for every person, alive or dead, there exists another person. This is going to be the parent. Let's say B and P, such that we have to interlace this back into the predicate. So the order we put in the input does matter. The thing that goes in first is the parent. So there's kind of layers to trickiness going on with example 5. We had to define our domains of discourse. If you left them off, then the problem will still work as before, but you need to be really careful with how it's written over here. But now that we did say the domain of discourse, B should come in first. Let me try to change my notation here. Lowercase p. B is the parent to A, the person. So the statement, every person has a parent, is written out this way. For all people, alive or dead, there exists another person, alive or dead, such that that person B is a parent of the original person A. So we did it, folks. That's rewriting this whole thing out as a quantified statement. Definitely kind of tricky. Any questions or comments at all, folks, getting that one down? Okay, I would say this is absolutely true, depending on how far you take the logic on this, how big you consider that set. But this one looks like it'd be something that is definitely false. There's a person who's a parent of everyone. Though, aside from its falseness or truthness, we just want to write it down using quantified statements. It says there's a person who is a parent. That means that there is going to be an existential, and it's going to be relative to the set P. Exists B in P. Now, that person is going to be a parent of everyone, so the next part is for all A in U. We're not talking about everybody being related, having some kind of relationship with this B. Then we write down the statement. Person B is a parent of person A. So B, P of B, A would be the statement there. And when you really look at these, really they're not the same whatsoever. All we somehow seem to have done is change the order of quantification. If we flip these, meaning is radically different out of nowhere. Part A is true, every person has a parent, but part B is saying for every person alive or dead, there is another person who is a parent to all of them. Again, depending on how you view this logic, to me, this one looks like it's the one that's false. But the bigger takeaway is statement A, statement B, radically different statements. And all we changed was the order of the quantification. Oh, and ran out of time as well. Sorry about that, folks. But any last questions with this one here before we call it a night? Okay, well, we got through it, folks. We'll come back, finish off the application problem down below, and next time we'll be in chapter 4 right after that. But have a great night, folks. I'll see you all in Wednesday's class.
Professor, may I ask a quick question?
Yeah, absolutely.
So from the last section, I'm not sure if I'm getting the implication modifier and the and modifier confused. So can I give you a theoretical prompt in English and have it written out and see if I have it correct?
Yeah, absolutely.
Okay,
How does it
so
go?
if it was the English phrase, I don't know, all cooks cook, I guess, or are cooking.
All
Then,
cooks.
oh, sorry. And if the cooks were, I don't know, A of X and cooking was B of X.
Okay, gotcha.
All right, I just want to make sure that I have this right when using both. Okay, so because we have all the cooks, we have the universal modifier of X
Yeah,
in such that is it, so the first situation is it would be A such as or such that A of X and B of X, or would it be A of X implies B of X?
I would say this one ought to be the implication, but let's think about that real quick here.
Okay.
A of X implies B of X. Let's see. All cooks are cooking. You know, that almost seems like an and. Let me think about this. A of X says you're a cook, then you're cooking. Hmm.
Or
So
could it be
cook,
either one, I suppose? I don't know.
let's view it from this.
Okay.
All X, you're both a cook and you're cooking at the same time. So all cooks are cooking.
Okay, that makes
Hmm.
sense.
Kind of seems to be about right. But usually for these, it often implies an implication. So let me double check another one over here. Thank you for that. Let me
Yeah,
compare it
thank you,
against
Professor.
this one. Or, yeah, it's kind of in the same spirit of this one, right? So
Okay.
what's this? So when it said all accountants own Porsches, here we said with the for all, if you're an accountant, then you own a Porsche, but versus for all X, P of X, and Q of X. This statement over here on the right is saying for all people X, they are both an accountant and they own a Porsche simultaneously. So this is a really broad statement. It's saying all people are simultaneously accountants and own Porsches.
Oh,
It's saying if you're an accountant, then you own a Porsche. So X could be either an accountant or not an accountant in this statement. Whereas
that makes sense.
here, this one feels a little bit different for some reason. I'm kind of drawing a blank on this. But, I think it has to do with this part. For all X is saying for all cooks. So cooks are already a part of this one.
Hmm.
Here, this is saying for all X, but X is just a person, any living person. And then we said, if you're an accountant, then you own a Porsche. But over here, we could just say that's for all cooks already, for all X. And this is saying you're a cook and you're cooking. It looks like from this statement, we really could have just compactified it to for all X B of X. So this would be the all cooks part right here. And this is the is cooking part.
Oh, okay.
So that would be one way to view it. Or if we move backwards and say, for all X in U, where U is all people, then we would have to actually use A of X, that A is a cook. All cooks are cooking. We can now say, for every living person, that person is a cook and is cooking. So that'd be the really, really broad statement. Whereas over here, for all X and U, we say A of X implies B of X. This time it's saying, for all living people, if you're a cook, then you are cooking. I still feel like, yeah, maybe this really does kind of tie into this one a little bit better. Because when we put in a domain of discourse here of all people, the statement A of X and B of X kind of feels like this one. We're saying all people are both accountants and drive Porsches simultaneously. But it really does feel like there's a hidden implication in this one. Just really hard to see it this time. But does that help out in spotting it?
Absolutely. No, thank you so much.
Yeah, absolutely. I'm going to leave this here on the notes because I feel like this is a tricky enough thing to just kind of leave here as an extra discussion. Thanks for asking about that one.